Let's start to see how we can implement an example of topology optimization in 2D using this code. For that, let's look at manuscript part 2, because this is the paper from which I've taken this example application. So if you open the PDF, and the example that we want to run, there's a bit of explanation of methodology. The example that we want to run here is this one, figure number 4. It's similar, but not exactly the same. Actually, the length that I'm going to use is 120 millimeters, and the height is going to be 60 millimeters. There is an imposed, so it's a system, it's a beam, it's a 2D beam on 3 supports. Each one is 1/10 of the length, and 1/5 of the length of the supports from the top of the beam is moved rigidly via an imposed displacement downward. So as a result of this central part will be compressed, and you can imagine that there will be a main compression being transferred to the support here, and then 2 compressions also being transferred at 45 degrees on these supports here. I have switched to my board here to draw again the same example. This is our beam. It's 60 millimeters in height, 120 millimeters in length, and then it has these 3 supports, each of which is L over 10, so L over 10 is equal 12 millimeters in length. And then the top 1/5 of the structure here, so L over 5, which is equal to 24 millimeters, is what will have an imposed vertical displacement of 0.4 millimeters. Now, the way in which we will treat this problem and the optimization problem we want to solve is that first we will discretize this beam as many individual particles. And these particles will form a honeycomb pattern through the system. We will give more details later. Now, each of these particles will have a parameter xi attached to it. And this xi is such that xi equal to 0 means that the particle does not exist, or more precisely, that it does not interact mechanically with any of its neighboring particles. Whereas xi equal to 1 means that the particle fully exists, meaning that its interactions, each particle will be connected with the neighbors through springs. Well, those springs are fully in place. We'll see later in more detail what this means, and you can also just read the papers which explain all of this. Now, the objective of the optimization is to start with an initial value for each particle that is between 0 and 1. In our example, we will start with xi initial equal to 0.3 for all particles, discretizing this beam. And then we want, during the evolution of the optimization process, we want some of the particles to give away their xi and transfer it to other particles. And eventually we want only some particles, precisely we want that f equal 0.3, so the 30% of the particles in the simulation, so 0.3 times n, where n is the total particles in the simulation, particles with xi equal to 1, and we want 1 minus f, which is 1 minus 0.3, times n particles must have particles with xi equal to 0. Actually, it's not going to be exactly 0, it's going to be a xi min very small, but not exactly equal to 0. It's going to be 10 to the minus 3, if I remember. This is a condition that, again, you will see discussed in the papers, in the PDFs. But the idea is essentially that you start from a system where the xi, this existence parameter, is evenly distributed on all the particles, and then it gets more and more concentrated only into some particles. Which particles? Well, those that contribute the most to the transfer of the load. So you can imagine that the particles here in the center will be important because they transfer the load directly to a support, and as well there could be some particles in the diagonals here that are important. And just fast forwarding to the end of the example that you are going to see together, this will be the result that you will obtain. And you see that with this result, indeed, we start with the homogeneous domain, where all the particles are gray, and if you look at if we increase here and hover the mouse, you see that there is a 0.3 xi value down here. It will appear when I hover the mouse above. Xi 0.3, that's that initial value I told you about. And as we continue, as we run the simulation, you see that progressively some particles become darker. You see that there was a vertical displacement. Vertical displacement is the one that we imposed, this imposed U here, and as a consequence of that, the algorithm will be concentrating more and more the xi, which becomes darker and darker, so goes towards 1 in this color code here, into some particles, whereas the others tend to become white. And this is exactly what we were expecting, a main column centrally, where all the mass is concentrated, and then still quite some mass concentrated in the two diagonals that are transferring the load from the center to the supports, lateral supports. Okay, so the code is doing this. It's taking the mass of the system, whatever initial amount of mass, if you want to call it, or density or existence that you want to give. If you want only 30% of the system to exist in the end, then you start by giving to each particle just a 30% of existence by fixing the xi to 0,3, and then the code will converge towards a 0,1 solution, where 30% of the particles in the system have 100% existence parameter, xi equal 1, and the rest will have a xi equal to 0, or almost. Let me add one more thing about the geometry of the system, which will be useful later. The thickness of this beam here, so the third dimension that is not going to be simulated because this is a 2D simulation, we call it TZ in the manuscript. In this example, we will assume it to be equal to 1 millimeter. We will see later where this thickness becomes useful. In some of the inputs you need to know the thickness. In this example, we will work with the assumption that the thickness is 1 millimeter. You don't have to assume that the thickness is 1 millimeter. You could work with a system with different thickness as long as you will give the relevant inputs consistent with this decision of yours.